So I'm going to be talking about automating modular verification of secure information flow. First, let's unpack the title a little bit and talk about modular verification. Let's say we have a modular program with procedures F, G, and H, where F calls G, G calls itself, and G calls H. Let's also say that we have procedure summaries for these procedures. For example, we have that F has this procedure summary that abstracts its behavior, and similarly we have summaries for G and H that abstract their behaviors. We can now use these summaries in performing verification. For example, we can consider verifying a property of F, and in doing this, use a summary for G to abstract away its implementation details. We can similarly analyze G while abstracting its callees with summaries. You can imagine that for large programs, performing verification in a modular manner like this can help with scalability, since we can consider only a single or only a few components at a time and abstract away the rest of the program using procedure summaries. Now that we've talked about modular verification, let's move on to talk about secure information flow. Secure information flow is the problem of making sure that private inputs don't leak information to public outputs. For example, if we have this program P with public input L for low security and private input H for high security, we want to make sure that the private input H doesn't leak any information to public output O. The secure information flow problem can be formalized as a non-interference property. Non-interference is a two-hyper property, meaning that it's a property about two runs of the same program. Here, I'm going to copy the program P and prime all the variables to get program P prime, which will represent the second run of the program. Non-interference states that if we begin with the public inputs to these runs being the same, with L equals L prime, then the public outputs of these programs should be the same, with O equals O prime. Note that this should hold for all H and H prime, so if the private inputs can affect the public outputs, non-interference will not hold. In practice, non-interference can be too restrictive a property to expect a program to have. As an example, we can consider a password recognizer. The private input to the password recognizer is a user-provided password, and the public output is whether or not the password is correct. The output is clearly affected by the private input provided by the user, so we can't prove non-interference here as is. Still, we wouldn't like to leak more information beyond whether or not the password is correct. What we can do to still be able to prove that we don't leak undesired information is to allow for the declassification of some information. Here, we can declassify the information about whether the input is equal to the actual password and still be able to prove that we don't leak any more information beyond that. We've seen what secure information flow looks like at a high level, but let's look at an example program to get a feel for what these things actually look like. Let's consider this M-tree procedure main that takes as input an array A. This array and all its elements are considered private, high-security inputs. Let's ignore the call to init for now and focus on the call to outputter. Outputter is a procedure that, if called with an array A and I equals 0, will recursively call itself and visit the first 64 elements of the array A. For each element that it visits, if that element is equal to 0, it will print the element out. We consider this to be a public output of the program, and so we assert that the value being printed out is a public low-security value. As it is now, with us ignoring the call to init in main, this program has a leakage of private information from the array A to its public outputs. So now let's consider init. Init is another recursive procedure that, when called with an array A and I equals 0, it will visit the first 64 elements of A. For each element, it will declassify whether that element is equal to 0 or not. Other than that, init doesn't really make any changes to the array A. With this declassification, since outputter only prints out elements that are equal to 0, there's actually no undesired leakage in this program, and we'd like to be able to verify that. So let's look at how to verify non-interference. Two popular approaches are to perform a product program construction or to perform self-composition. Both of these approaches have the same high-level idea of combining both copies into a single program. Doing this turns the hyper property of non-interference into a safety property of a single program and allows us to use standard techniques for verifying safety properties. You may wonder about what happens in the case where our program P is modular and has several procedures. In that case, to do verification, we need to consider different interleavings. For example, we might need to consider this interleaving where the first copy is about to execute H and the second is about to execute G prime, or this one where the first copy is about to execute G and the second is about to execute H prime. While we may be able to use summaries for each of these procedures, none of our summaries will correspond to relational properties about the two programs, and so these will not be especially helpful for proving the overall non-interference property. The construction of modular product programs, which was proposed by Eilers et al. In 2018, involves constructing procedures that can be seen as per-procedure products. For example, here we have that a single procedure captures the behaviors of both f and f prime. You might be wondering if any of the behaviors that we saw previously are lost in this construction, since it kind of looks like we're not going to allow certain interleavings to happen, but this actually isn't the case because we have activation variables. So for each program copy, there's going to be a corresponding activation variable that is a Boolean value. And if it's true, that means that that copy can execute, and otherwise it means that it can't. So for example, here, if B is one activation variable for the unprimed program, and B prime is the activation variable for the primed program, then we wouldn't allow ourselves to run G because B is not true, but we would allow the second program to run G prime. If we learn summaries for the procedures in a modular product program, these can correspond to relational summaries about the original program. So here, for example, we might have a summary that relates the behavior of the two different copies of G and G prime. These summaries can be useful in proving an overall relational property like non-interference. For verifying modular product programs, we can, in theory, use any modular verifier for safety properties. An example of such a verifier is spacer. But if we do something like this in practice, we aren't necessarily going to succeed, and we will see that in our evaluation later. The problem here is that modular verifiers might not infer summaries that correspond to relational properties of the original program. In the original work on modular product programs, the summaries that were used were provided via user annotations. What we'd like to do is automate away the need for user-provided annotations. And in order to do that, we're going to first consider the types of summaries that would be useful to infer. And the insight here is that for non-interference, properties that involve equalities between corresponding variables, that is, the primed and unprimed versions of a particular variable, are useful. So, for example, if we consider this procedure in the modular product program that captures the behaviors of G and G prime, that has inputs B and B prime, the activation variables, as well as inputs W, W prime, X, and X prime, and outputs Y and Y prime, and Z prime, a useful summary that we might want to learn is this one. It contains both activation variables and relates equalities between the primed and unprimed versions of W and Z. Since both activation variables are true here, this corresponds to a relational property of the original procedure G and its copy G prime. So now that we've established that we want to learn summaries that have a particular shape, we can try to consider techniques for generating such summaries. And one obvious choice is to use syntax-guided synthesis. In syntax-guided synthesis, we can give a specification S and a set of syntactic restrictions R to a synthesizer, which in the case of program synthesis would produce a program P as output, or in our case would produce a summary P as output. This output P should be a witness for this exists for all formula, where P needs to obey the syntactic restrictions R and also meet the specification S for all possible inputs I. In our case, the specification that we would use is that the summary P actually over-approximates the behavior of the procedure that it is a summary for. A synthesizer can be implemented using a SAT or an SMT solver, and the syntactic restrictions can be expressed using a grammar. Generating such a program or a summary P can be done using a guess and check approach. It's an iterative approach, where at each iteration we generate a candidate that meets our set of syntactic restrictions, and this constitutes the guess part of guess and check. We then check using, for example, an SMT solver, whether the candidate meets the specification. If a candidate does meet the specification, it becomes a positive example, or else it becomes a negative example, and the next choice of candidate is influenced by the previous successes and failures of the previous candidates, and this lets us avoid doing some redundant work. Now that we've seen that we want to infer summaries of a particular shape and have seen a method for doing so involving syntax-guided synthesis, we can now describe the set of syntactic restrictions that we're going to use. We came up with 3 separate templates for inferring useful summaries for non-interference. The first of these templates is for generating quantifier-free summaries. These relate equalities of the inputs and equalities of the outputs and look like what we've seen so far. The second of these templates is for generating quantified summaries. These summaries contain universal quantifiers and are tailored for handling programs in which we need to reason about equalities of array elements across copies in order to prove non-interference. The final of these templates is for generating property-directed summaries. These summaries templates involve syntactic restrictions taken from the calling context of a particular procedure, which may contain declassification, and so these are useful for programs that contain declassification. So now let's discuss the generation of quantifier-free summaries. If we again consider the same component for G, we can take a guess and check approach and generate candidates, maybe learning one that abstracts the behavior of this component. The guesses that we make consist of 3 parts that I would like to highlight. The first is activation variables. We require that in all of the candidates, these activation variables are true, because that way the candidates would correspond to relational properties of the original program. The second part of the guesses are the input equalities. These consist of a conjunction of a set of equalities between the primed and unprimed versions of the same input variable. The final part of the guesses is the output equalities on the right-hand side of the implication, and this consists of a single equality between the primed and unprimed version of one of the output variables. We can now talk about generating quantified summaries. As I mentioned before, these are tailored for arrays, so in this case, let's assume that y and y prime are arrays. A possible candidate that we would generate is something like this, and again, I'll highlight the important parts of this candidate. The first part is the quantified variables. These variables are going to be used later as array indices. The next part is the range formula. The range formula restricts the values that the array index can take on. Here it only restricts the unprimed version, but if we look at the next component, the equalities part, we can see here that I and I prime are equal, so the range also restricts the values that I prime can take on. If we look at other things that are in this part of the candidate, we can see that we again have that activation variables are both true here, and we also have equalities of the primed and unprimed versions of some of the input variables. Here, w equals w prime. Finally, on the right-hand side of the implication, we have the cell property, which consists of the ith and I primed elements of y and y prime being equal. The final kind of summary that we're going to consider is property-directed summaries. I won't have time to discuss the syntactic requirements for the summary here, so please look in the paper for details about that, but I will describe the main idea behind property-directed summaries now. As you might imagine from the name, property-directed summaries take the property that we're trying to verify into account. So here we have the same property as before, where we assume that the public inputs are initially equal, so L equals L prime, and we want the public outputs O and O prime to be equal at the end. So the way that this is going to work is that we will assume that this property doesn't hold, and then try to infer a summary that contradicts that. So here we're again going to focus on the procedure that contains the behaviors of G and G prime. So we're going to abstract away the remaining procedures using their summaries, and use these summaries to propagate the negated property to be about the inputs and outputs of the procedure we're considering. We'll use that to come up with a context. And now that we have the context, we want to infer a summary that contradicts that context. If you're familiar with how CHCs like spacer work, the idea is very similar, except here, instead of relying on an interpolating solver to give us the summary, we use syntax-guided synthesis so that we have more control over the shape of the resulting summary. Now that we've seen the three different summaries we can infer, let's look at how we can combine them into a verification algorithm. First, we infer quantifier-free and quantified summaries. Then we try to perform verification using these summaries. If we fail to verify the program and don't find a counterexample, we then learn property-directed summaries and again try to verify using the updated set of summaries. This continues until we eventually succeed at verification or find a counterexample. We implemented this algorithm in a prototype called Flower on top of the Freecorn CHC solver, and we evaluated it on 29 benchmarks. 21 of these benchmarks were based on the benchmarks used in the original work on modular product programs. 2 of them were based on S2N, a TLS implementation by Amazon Web Services, and 6 of them were taken from the evaluation of Blazor. Our tool is able to solve all of these benchmarks without any annotations. Note that the annotations from the modular product program benchmarks were removed in our evaluation. We also compared our tool against 2 other tools, the first of which is Descartes, a hyperproperty verifier. It was only able to take 10 of our 29 benchmarks as inputs because it didn't support declassification or properties involving arrays. And of these 10, it was able to solve 5. It wasn't able to solve the other 5 because even though it also uses a template-based approach to infer invariance, the templates that it uses are not well suited for non-interference. We also compared against Spacer, which is a CHC solver, and Spacer was able to solve 14 of our 29 benchmarks. We found that Spacer's interpolation was often unable to find suitable summaries in the case of programs that have recursion, and Spacer was only able to solve 5 of the 20 benchmarks containing recursion. We also found that Spacer's performance on some of the examples was affected by the size of the array in the example, and here we can see that behavior in this plot. Along the x-axis for a particular example, we have that the array size used in the example increases, and along the y-axis we have the time taken to verify the program in seconds. Note that this is on a log scale. So we can see here, so Spacer is shown in purple, that Spacer performs much worse as the size of the array increases. Meanwhile, Flower, because of the templates that we use, is not too affected by the size of the array. Something to note is that Spacer is actually able to find quantified invariance. It just doesn't find the ones that allow it to scale for this example. There's a large body of work related to what we've done here, and most of that falls under 3 main categories. The first category is that of relational program verification. Most of these approaches, especially those that are more automated, are not modular, and more modular approaches, such as the original work on modular product programs, are often less automated. A lot of effort has also been put forth into constructing product programs that make verification easier, but most of those approaches do not derive relational procedure summaries as we do here. The second category that I want to mention is information flow checking. We've seen that information flow checking can be reframed as non-interference, so there's a large overlap with the first category, in which many approaches are not modular. Other than those approaches, there are modular approaches that use, for example, security type systems, as in the classic work by Denning and Denning and Volpano et al., And there's also been work on using dynamic taint analysis to do information flow checking. These approaches often aren't path sensitive and as a result suffer from imprecision. The final category that I want to mention is syntax-guided synthesis. Syntax-guided synthesis has been applied to many domains to infer loop invariants, termination conditions, and so on, but to the best of our knowledge, it hasn't been applied to inferring relational invariants for proving non-interference. A particular effort in syntax-guided synthesis that I would like to mention is Fedyukovich et al.'s 2019 method for generating quantified invariants for arrays. We've adapted that here to allow us to infer quantified summaries. We've seen in this talk that non-interference properties are very structured, and that the structure allows us to automatically infer useful summaries with syntax-guided synthesis. To do that, we proposed 3 kinds of grammar templates for proving non-interference, including ones that allow us to infer quantified invariants. We believe that, even though we focused on non-interference in this work, the same approach could be applied to allow for modular verification of other hyperproperties.